Good afternoon, everybody. So, continuing with the last lecture. So, today I'll be discussing the different methods which actually were implemented after the boundaries were actually started to be considered as either parabolic, as I showed you in the last class, or even in some cases trapezoidal also. So one of the first methods that used a proper analytical technique was the area deviation method, which was actually introduced by Jamieson and Hacker. And then it was actually modified and made better by Zhao and Lapierre. Now, in area deviation method, basically what they implemented was they used BREP as the modeling technique, and for any non-manifold problem, they actually started giving a tolerance to the sectioning plane, and the axis of sectioning was considered to be the z-axis. The axis of sectioning, where the sections were going to be created, was considered to be a z-axis. And what they also further did was the slicing algorithm actually started with the introduction of the dimensions or the coordinates, rather vertices also you can call them, either coordinates or vertices of the complete solid. Now you had a base, and then you had a height of the part. So once you had a base and a height of the part, it could very easily be found out which is the lowest point of the part and which is the highest point of the part. So with respect to origin or with respect to a plane, you could easily find out which is the lowest part of this component, lowest point of this component, and which is the highest point of this component. Now, based on the lowest and the highest point, a slice was going to be decided in Z axis. Now, one slice actually is going to be represented by a block, like a triangle, basically. So if you have something like this, so when you cut it into half, so this becomes the first block and this becomes your second block. Now, there was an option of either using uniform slicing, and they also implemented an idea of using adaptive slicing. So I am going to discuss the adaptive slicing and how it became better. So in adaptive slicing, basically what they said was that there may be some features or there may be some deviations due to manifold and non-manifold conditions in the solid. So when we are cutting the solid into slices, this is the area deviation that is allowed. So what will be the area deviation? So the area deviation will be the area of the I plus 1 slice. This is I plus 1 and this is ith slide. This one is the ith slide. So area of the I plus 1 slide minus area of the ith slide divided by the area of ith slide, and that ratio should be less than or equal to delta. Now what is the delta? Delta was considered as the correction factor or the tolerance that was allowed for the solid model to be deviated during slicing process. I explained that in when we were discussing the area method in the earlier lectures, that when you are doing some slicing operations and you are losing some critical features, or even if you are not losing some critical features, even if you are slicing across the cross section, what happens is, if you go for adaptive slicing, due to different number of slices and different zones, there is a loss of volume because of shrinkage, generally because of shrinkage. So when the loss of volume is going to happen, it is also going to be reflected in terms of the cross-sectional areas of the two slices. It is also going to reflect in the cross-sectional area. So the ratio of that cross-sectional area of the two consecutive slices has to be within a defined limit. And that defined limit was considered to be 5%. The defined limit was considered to be the 5% of the original surface area. So whatever the original surface area was, that you can easily find out because you have a CAD model. So once you get those two slices, you cut those get those two slices, and then you find out delta, sorry, sigma. So once you get sigma and you check with respect to delta, if this condition is being satisfied, then the slicing is correct. If this condition is not satisfied, then you have to go for reslicing. You have to go for reslicing. Or you can go directly to an adaptive slicing procedure where the zone where this is not happening, suppose in this zone, if this is not happening, then you can go for adaptive slicing also. You can go for adaptive slicings also. So the problem with this method was that the thickness of the layer remains between maximum and minimum available in the RP system. It will give you a sort of value in between the maximum and the minimum range, but it will never give you the optimal value of the surface layer thickness that you can take. It will always give you an approximate value, say like your range is say 100 to 500 micron. It will give you an answer of like 200 micron or 300 micron, but it will not be giving you the exact optimal value. So what Zhao and Lapierre basically did, they implemented the same concept but introduced, using the AutoCAD runtime extension and C++, they introduced an optimization algorithm into the system, and that optimization algorithm actually started to help out with respect to the layer thickness. But still what people found was that the answer never used to come out very specific. The answer was still in the what you can call as the assumption ranges. It like the answer started coming like 270 to 280, something like that, but still you didn't get the exact value. So in order to go get the exact value, you needed to do a lot of experimentation. So Kulkarni and Datta in 1996 basically came up with a new method in order to contain the surface roughness and the stair casing and the product quality. So as you already know that for a CAD model, at any point there is a normal vector and there is a curvature. So normal at any point can be approximated as a circle, and that approximation will give you 12 expressions. Now those 12 expressions has to be, when analyzed, will give you different geometrical conditions, and containment requirements has to be considered. So the surface normal has to be taken with respect to the curvature now. So what they did was this, that for any point, P, the slice thickness was actually defined as a function, and the function was rho, theta and delta. So what is rho? Rho is the vertical normal curvature that you can find out using CAD. Theta is the angle between the horizontal and the normal vector. So suppose if the normal vector is going in this direction, so with respect to this axis, what is the value of theta? So this gives you the value of theta, and delta is the allowable cusp height. So delta is the allowable cusp height. So now the layer thickness is basically a function of cusp height, angle between horizontal and the normal vector, and the vertical normal curvature. So in order to find the slice thickness, they assumed two approaches. That is the maximum curvature approach and the minimum layer thickness approach. This approach is actually dependent upon CAD function. This approach is actually dependent upon the CAD function, where the surface geometry is now going to be calculated using the maximum principal curvature and minimum principal curvature. And this function was actually analyzed, and it was found that this was inferior to the minimum layer thickness approach. It was inferior. And what they did was, in order to maximize or minimize, that is basically, I'll call it as optimize. In order to optimize the function, they used sequential quadratic programming algorithm, and MATLAB was used to solve the optimization. It was SQP algorithm of optimization, and MATLAB was used to solve the problem. So What they found out was that directly you cannot get the op- optimal layer thickness. Directly it is not possible to get the layer thickness in an optimal range. So what they did was they actually slicing procedure was carried out in two steps. The first step, they used the model to divide it into distinct sectors. Why distinct sectors? So that if a model has any feature which cannot be left out, then that part should not be missed in the approximation range. That part should not be mixed in the approximation range. So what they defined was a distinct value of layer thickness, which basically incorporates all the critical features of the part. And then in the second step, what they actually did was, once you had sliced the part, they started to look for the cusp height. Now, wherever the cusp height was within the specified limit, that layer was left as it is. And wherever the cusp height was found to be going beyond the acceptable limit, those regions were re-sliced or basically went into adaptive slicing. The advantage of this process was actually this, that now what the slicing that you actually obtained was based on a mathematical number, and that mathematical number could be easily optimized, and the slice thickness for each layer was now a specific number rather than a range. With the help of Kulkarni and Datta's work, we could easily get out what will be the specific number of the layer thickness, or what will be the specific height of the layer thickness that can be used basically in order to create a part for every section. So now suppose if you have a part like this, if you have a part like this, now this is one section and this is another section that needs to be somehow maintained, so in order to do that, what they told was that this is the range where no critical feature comes. So this is one area. This is the second range where all the critical features come. And this is the third range where no critical feature is there. So initially you just divide these like this. For here you can define like this, and now you check for all the values of cusp height. So if the cusp height of this section, is coming out to be within the specified limit, then there is no need to change the layer thickness. However, if it exceeds the allowable cusp height, then you need to go for adaptive slicing. Now, sloping surfaces consideration, this was done by Hope, and it was a part of a very big work that Hope did actually from 1997 to 2002. And this is one of the first things that he actually proposed. So, what Hope did was basically the pioneering work regarding the slice edges and on the slice contours. So he was the first person to have sloping build edges rather than the rectangular edges. He was the first person to give this idea that the edges are not rectangular in nature, but rather they have a sloping edge. He did not define it exactly as a parabola or something with a specific name, but he said that the edges are not something like this, rather the edges are something like this. So edges are something like this. So the idea was completely different to what earlier people used to say, that the edges are rectangular in nature and we are going to cut the edges into rectangular shape and then go for post processing. What Hope initially started saying was the edges are actually not like this, but rather like this, which have a slope. And the idea what he proposed was that, first of all, it gave a better approximation. It gave a better approximation. And secondly, the surface finish was vastly different. The surface finish was actually vastly different when it is approximated as a rectangular edge and when it is approximated as a sloping edge. What he said was that the surface roughness of this profile will be lesser as compared to surface roughness of rectangular profile. So a sloping edge will actually gives you a better approximation of the whole building process. So what he did was he used multiple B-spline surfaces from IGS format in order to define a part. Then they slice the model by tracing the surface contours and computing the cutting direction as the number of points specified by the user. Like if you have a sphere like this, if you have a sphere like this and you cut that into sections, you cut that into sections. So what you will observe from this view, what you will observe from this view will be a circle, a bigger circle, a bigger circle, then maybe a smaller circle. So the surface contours were actually defined over here, and putting these contours or corresponding cutting vectors in order to generate a CNC code. So the contour geometry was defined, but the contour geometry was defined, and the cutting direction is the this axis, which is the Z axis. The cutting direction is the Z axis. Now, based on the contours, you could define the X and Y axis movement, and Z axis was actually adopted with respect to the layer thickness that we were taking. So the Z axis height was approximated equal to the layer thickness that we were going to take. What happened over here was generally the layer thicknesses were coming out to be almost uniform. Very minor variation was happening because more emphasis right now is on the edge profile, and this edge profile and the contour. So slicing was generally in a uniform standard. So in 2000, he again proposed a new method of adaptive slicing with sloping surfaces, which could in fact not only better the surface quality but also reduce the build time. He proposed a new method where adaptive slicing was now with the sloping surfaces. So what happened was, not only your surface quality was becoming better as compared to the rectangular edges theory, also due to adaptive slicing coming into picture, your build time was also getting reduced. But in order to compare the two systems, we needed some parameters. So he took basically two types of errors, that is the cusp height and maximum difference of the plane layer in the plane layer. What is the maximum difference in the plane layer? Now, suppose if you have a part like this, you are cutting. So this is the layer. This is the layer that you are generating. Now, if you cut it, say like this, the layer thickness reduces, and that difference is taken as the consideration. Rather, this can also be called as delta. This can also be called as delta, where delta is the difference between two layers using two layers considering cusp height. So they developed a relationship. They basically developed a relationship for the whole function. And these are the two formulations that they developed. So delta is for cusp height and epsilon is for the maximum difference. So these are the two expressions they basically developed, where RC is the radius of curvature, T is the layer thickness, alpha is the angle between horizontal and the normal. Now you have an option of optimizing either of these two functions. Now you have a chance of optimizing either of these two functions. Generally, what people did was they optimized the cusp height For two reasons. First, the function is easier to understand because it is basically based on the radius of curvature and the layer thickness. So it becomes delta with respect to t was very easy to optimize because radius of curvature and alpha both are known quantities and both are generally going to be constants. So optimizing this function was easier. Now, in adaptive slicing, they also went even further and they went into module slicing, and the CNC code generation was done for each of the module slicing. So what is module slicing over here? Module slicing is nothing but section wise slicing. Suppose I have a part like this. So each section that I'm going to consider with respect to the layers is a specific module. So that module was basically programmed separately. And now if I want to break it better, I will make it like this, I will make it like this, but keep all the other layers as constant. So in order to convert that module into something which can be easily understood, that is the CNC coding of the head movement. So each section was named as a module, and these sections were glued together to form a prototype. So this becomes module 1, this becomes module 2, this becomes module 3, and this becomes module 4. So each section was module, and each module had its own CNC program of the head, which basically gave you the idea where the head is going to move in order to deposit the raw material. The advantage of this process was basically first of all, the edges were considered to be sloping in nature, and secondly, the function was a mathematical expression based on some real-time data, and the optimization of this function was far easier as compared to other functions, even better than Kulkarni and Datta. But Kulkarni and Datta and Hope's work are the basis on which today's algorithms actually work for finding out the optimal layer thickness. These two are the most simplest and basic algorithms on which basically all the free softwares that we have in today's environment basically work. Now, based on what Hope suggested, Money and Cormier also came up with an idea of region-based adaptive slicing. Now, region-based adaptive slicing was basically nothing but you basically divide your CAD model into specific regions based on their importance, and the value of the maximum allowable cusp height. Now, based on that, you could first identify the critical surfaces with the help of cusp height requirement. Then what you do was all those layers which were coming within the range of specified cusp height was kept constant and selected as it is. And the other layers which were going beyond the cusp height were being brought back and re-sliced. The region that Money selected was actually picked up from the concept of fast interior and accurate exterior, where if you remember, we had two different zones and each zone had its own slicing and filling algorithm. So slicing two regions basically was taken up from Sobrun's idea, and based on these two concepts where region wise slicing and the interior and exterior wise slicing was done, and finally you did an optimization basically based on which is the value of layer thickness which is coming out to be the most common value, and that value was selected as the optimal value for the layer deposition. The idea was very prudent because it also takes care of your build time, but the idea was not very popular because you needed to do a lot of computation in this process. You need to do a lot of computation in this process because first you will go about having a coarse slice here, that is the thicker slice. Then you will go on refining those slices till you get all your values below the allowable cusp height. And now once you have all the values below the allowable cusp height, now you will go about sorting them and finding out the value which is going to be repeated in most number, and that value will be taken as the cusp height. So this process was there, but this was not selected. Another process was adaptive by Wayne and Perrin in 1999, and it used a non-rational B-spline curve, which is the most robust curve that has been developed in the surface modeling. NURBS is one of the most robust curves, and it uses basically the surface geometry and the curvature of the normal radius of curvature and the n vector, which was obtained, which was also taken into consideration by Kulkarni and Datta. So what they did was they started with the slice thickness that was like taken with Kulkarni and Datta, and then based on that they again started working on these sections, and rather than breaking these sections into uniform slices, they again broke the surfaces into variable number of slices. That is, the slabs were not in uniform cross section. The slabs were basically defined with respect to a predefined cusp height. So what you said was that for any given CAD model, the value of delta that I'm going to accept is 1. That is the precondition that you have already said, that the value of delta that you will accept is 1 or below. Now, you simply went and divided the whole CAD model into number of slabs across the z-axis. Then using the slice thickness formulation of Kulkarni and Datta, you analyze the slice thickness of each and every section. Once you got all those sections together, now you check for pre-specified cusp height. All those layers or all those slabs which are satisfying the pre-specified cusp height, they are taken as one region and all the others are taken as the other region. All the other region will now be cut again further, and then what you will do is, once you have all the slices ready, then you go for the hatching. Now what is hatching? This is a new term which has come. Suppose this is the contour of a layer in xy axis. Okay, this is your x axis and this is going to be your y axis. Now how will this hatch be filled? The head will actually move like this. Okay, so this is how this hatch will be filled. Now there are another way of doing this. This is hatching along an x-axis and this is hatching along y-axis. So what they did was they devised a method where every alternate layer was hatched in a particular axis. Like the first layer was hatched in x-axis, the second layer was hatched in y-axis, again the third layer was again hatched in x-axis. So what they found was that with adaptive slicing and selective hatching, actually three things started happening. First of all, the shrinkage became lesser, surface quality became better, and build time also started to reduce. So all the three basic criteria were somehow getting fulfilled. As I explained earlier in class also, surface quality or the strength basically of the part became better, shrinkage became lesser, and build time also reduced, because now you are not filling completely 100%. You are not filling 100%. Actually, you end up filling only around 60 to 70%. 60 to 70% only. So since you are only filling 60 to 70%, even on the thickest layers, the time for internal filling was reduced. So selective hatching actually gave you the advantage where your time was getting reduced, and alternate hatching where X and Y were alternated gives you better strength and better bonding.